Hello, everyone. Let's wait for people to join here. Can you see the screen? Can you see like in all my slides? Okay, great. Just few more seconds for allowing more people to join the lecture. I see. Yeah, thank you for reminding me. I just copied the test, the practice test from last year. So are you able to join? Okay, so are you able to look at the exam or not yet? No. Okay. Sorry, guys. Let me do that right now. Okay, quizzes. Restrictions. Okay, so okay. Save and close. So I did change the date. Thanks for that. Okay, the most important thing about the mock-up test here is being able to visualize the style of the test and be familiar with adding the file when you finish writing the answer. Just make the basically a scan of your answer and upload it to the specific location on the quiz. So you have a lot of time to do this, and it's multiple kind of you can attempt to solve the exam as many time as you want. Just before I start, I would like to ask you guys one thing about some volunteer work needed for this course. I posted some time ago a note about note-taking volunteer needed for this course. So some of your friends needed some help with that. I would really appreciate if you can step forward and provide this help. That would be great. Looks like maybe the announcement was not spread as much as I wanted, but I'm here just reminding you guys, if you can consider this, would be greatly appreciated. Okay, so let's start today's lecture because we're kind of falling behind, but again, I'm not worried so much about that. I'm trying to make sure that you guys understand those fundamental principles that we are covering in this course. So far, we are kind of getting into the topic. So that's why we are moving a little bit slow on that, building the knowledge about how to treat and how to analyze fluid mechanics in an engineering system. Chapter 3 is talking about the fluid flow analysis. And as I mentioned, chapter 3, 4, and 5 is kind of giving you an introduction to how can we deal with fluid flowing in the system. So last lecture, we spent quite enough time looking into the conservation of mass, or what we call it the continuity equation. And if you remember, we solved a few examples on this. And the last part of the example that we were talking about at the end of the lecture, we didn't complete, but let's get back to the same point that we were talking about since last time. Some people were asking questions at the end of the lecture last time. looking into this problem here, and you know, some of you are saying, oh, the flow is coming in to the pipe at this location here is basically you know, steady, right? Because the velocity here is constant, the area is constant, so there's more kind of a steady flow coming in, and there is a steady also flow going out. Okay, how come we do, you know, we assume that this problem is an unsteady problem? Okay, the thing is, you remember that we were talking about the system that we, you know, basically select in our analysis. So the system that we selected here, we call it the control volume here. This is my control volume. Okay, so this control volume could be like this, could be even all up to this point. Yes, there is flow coming in and steady here, and there is a flow going out steady here, but there are some difference between this flow and this flow that is basically supplying this tank. And the system I'm considering here is the fluid level inside this tank, right? So within my control volume, there is an accumulation of the mass in the tank. That's why we will have to consider, like, you know, this accumulation. And this is basically the, you know, what is required in this question. So it's asking you to estimate the time required to fill the remainder of the tank, starting from an elevation of 0.3 meters and going all the way up to, you know, 1 meter, which is the complete height of this tank, right? So if you remember, we started by the analysis using our general conservation equation for mass, and this is basically the mass of our control volume with respect to the time is equal to the summation of the mass coming in minus the summation of mass going out. And I mentioned last time also that you might have multiple streams of fluid coming in and multiple streams going out. In this specific problem, we have only one flow coming in and one stream coming in, and one is going out. Okay. So if we put this, you know, if we put this equation now, the mass of the control volume, we know that the mass of the control volume is basically what? It's the volume, right? Multiplied by the density, right? But the volume of the tank, the volume of this mass that is inside the tank is kind of changing with time, right? So that's why we took, like, you know, a specific, you know, a distance h at a certain, or like at a general location where this level of the water is at. So we have h here and the area of the tank. So area of the tank times h will give you the volume. If you multiply it by the density, it will give you the mass. So, and this is basically what we are kind of, you know, explaining here, right? So this is a volume and this is the density, right? So d of this whole mass by dt is equal to the mass coming in. What is mass coming in? Is, we know that this is a velocity, and we know the mass is, if we have an average velocity, what will be the mass? Looking at the chat here, so people, if you guys can be a little bit more interactive, so we can move faster. What will be the mass of the flow coming in? Anyone? No one want to participate? So density flow. Okay, density times the flow rate. Yes, the flow rate is the area times the velocity. Okay, so I think I need to move faster. So anyway, so rho times the area at 0.1 and the velocity at 0.1. The velocity is given an average value. The area is also given in this problem, as the diameter of this whole pipe is 12 centimeters, right? And the density here, if you remember, this is water, so density is constant, right? And what is the mass going out of this system is basically, you know, the velocity at, you know, at the exit here, which is V2, and the density times the area 2, which is happen to be the same as area 1. So rho, A2, and V2. Okay, the area is rho. The area is pi over 4 the diameter of the pipe square times V1 minus rho pi over 4, the diameter of the pipe square V2, right? Looks like a pi over 4 here can be gone with all the, the equation. And then we have also the density is constant, right? So what is left here is basically, d of and the d square of the tank is a constant value. So I can actually divide this whole equation by d, right? So in this case, I have dH by dt is equal to 1 over d square of the tank, right? And what is left here is d pipe square times V1 minus d, d pipe square times V2. Okay. So I know what is V1, I know what is V2. V1 is 2.5 meter per second. V2 is 1.9 meter per second. The diameter of the pipe is 0.12 meter. The diameter of the tank is 75 centimeters, so 0.75. It looks like all these part here would be basically, can be calculated. So I have this is calculated as 0.0153. This is equal to dH by dt. So I have the variation of the level with respect to the time is equal that, right? So if I need to find out the time required in order to fill the tank, I can just, do the integration. So the integration here will be with respect to the time because I need the total time. But it looks like, this is d by dH by dt. So I can kind of, separate the variable here. So I have dH is equal to 0.0153 dt. So if I need to find out the total time, I should integrate from 0 to capital T, where h started at time t equals 0 at a level of h that is h1 is equal 0.3. And the time total, or the time to fill the whole tank, the h now is 1 meter, right? So it's going to be a very straightforward, integration. So this will be h, and the limitation is 0.3 to 1 is equal 0.0153, and then t minus 0 here, right? So I can find out t in this case, and t will be 46 seconds. Okay. So any question on this? Yeah, the pressure here has no effect on our calculation here. We're talking about mass, right? So whatever condition coming in and going out, the difference between the flow rate in and out will be basically filling the tank, right? Of course, in reality, if you are observing what's happening, you might see less flow coming in because of higher pressure at the top of the tank. But this has nothing to do with the analysis here. We are doing conservation of mass, and the conservation of mass equation does not include the external effect of the forces. Okay, but it is a good question because this is our second part of today's lecture, which is talking about the momentum. Okay, the momentum change, conservation of mass. This is basically the first part of this chapter. The second part will be the conservation of momentum, and the conservation of momentum include forces here, and of course is going to be including also pressure if we have pressure forces affecting our system. So this is a good question. So example 3, I don't think I have time to go over this, but this is giving you an idea about when we have multiple streams. So apparently here, my control volume here is something like this. This is a control volume. Okay. There is stream coming into this control volume, and there is two stream. We don't know, like, there's could be out here and out here. It looks like the arrow here is showing it's out, but you might have something coming in here and also going out here, right? So, but anyway, let's stick to this problem here. So I have the diameters, so I have the area. So I have A3, I have A2, and I have A1. So gasoline enter a section 1 at 0.5 meter cube per second. So Q1 is given, is 0.5 meter cube per second. It leaves section 2 at an average velocity of 12 meter per second. So it leaves section 2. So the velocity here is given as 12 meter per second. He's asking what will be the average velocity at section 3. Okay, so find out this V. So first of all, right, this is gasoline. So I can find out, for example, the gasoline density if I want, right? But assumptions is very important here, that the density is constant, right? Because this is liquid. So it doesn't matter, like, if I need to find the density or not. Why? Because mass N equal to mass out, or volume N equal, or volume flow rate N equal to volume flow rate out, because I can divide the whole equation by the density, if you remember from the last lecture. So I can say, for example, here, dm of the control volume with respect to the T is equal to summation of mass N minus summation of mass out. Okay, so what do you think about this problem as a second assumption here? What other problem in order to solve this equation? Other, assumption, very important. Incompressible, it's done. Okay, steady state, right, or a steady flow, right? So steady mean d by dt is equal 0, so which means that this term will be gone, right? You don't see any, option here for the fluid to be compressed inside the system, or this inside this control volume. Whatever coming in is going out. So within the system, there is no variation inside this control volume, right? So it is a very valid assumption here. So it's almost like a junction box. What is coming in is just going out, no accumulation inside, and no mass change of the system. It looks like very simple here, the mass N equal to, of course, summation will be M out. Out here is actually 2, and N is 1, right? So I can say, for example, I can divide by density, right? So it's going to be Qn is equal to Q out. Why? Because density is constant. Okay, so Q out here will be Q2 plus Q3, and Qn here is only Q1. And you can actually do the rest because it's very simple, just substitution. Okay, so let's get into, another part of our lecture, talking about, the conservation laws that is governing the fluid flow in the system. The first one that we kind of, discuss is a conservation of mass, right? And we studied this. The second one is basically the conservation of momentum, okay? And we know that basically in order to relate the momentum in any system, we have to find out what is actually, changing this motion of the fluid or the object that we're talking about. Of course, in your solid mechanics, you've studied this as, forces applied on a certain element or a body that is rigid body or something. In our case here, we have a fluid, okay? So we need to find out the same thing. We need to find out the forces applied on the fluids in order to, or these forces that is, changing the momentum of these fluid inside this system, okay? So we're still going to apply the same, Newton's second law, because the Newton's second law is basically dealing with the summation of all the external forces on any system is basically equal to the change of or the rate of change of the momentum inside the system. Okay, so you might have seen this many times, right? And even in our course this year, we talk about this. But before, it was like, if you remember, the summation of force equal mass times acceleration. Acceleration was 0 in the statics chapter, right? Here we have an acceleration that cannot be ignored because the fluid is moving, right? And the fluid is moving, maybe it could be moving with variable velocity, right, with time. So in this case, in general, I can say that the summation of force is equal to mass times acceleration, right? And the acceleration, if you remember, acceleration is the change of the velocity with time. So this is velocity. I know we have so many V's here, but this is time. Okay. And if I am talking about a specific certain mass of this system, right? So I can say, for example, MA is M dV by dt. And if this mass is constant, I can just take this mass and just just go after the derivative operator. So it could be dmv by dt, right? So the acceleration, the mass times acceleration here is basically, this is the mass times acceleration will be dmv by dt. mv is the mass times the velocity, is what we call it the momentum, okay? So which means that in this case, the summation of forces will be the change of the momentum of the system with respect to the time. Okay, so this is just a basic definition of what is acceleration mean. If you remember last time when we talk about the control volume, we said there's something called boundary, and this boundary is what we draw around the system, and we see what's happening inside the volume, inside the control volume, and also what we see around, around the system, or at what we call it the boundary lines or the control surface. Okay, so same thing here. If we are looking into see the forces and the momentum, so we are talking about like what forces affecting these control volume. So if we have a certain control volume here, this is control volume, okay? We call this is control surface, okay? And now we have some forces acting on this control surface. And there are some variation of this mass of the system, okay? So whatever forces acting on the control volume, it will change the momentum of of the mass of this within control volume. Now we can look into, the component of these forces. If you remember, like in our solid mechanics, when we are dealing with a general force in general direction, we can take the component in X direction, Y direction, and Z direction, okay? So you will see the equation for the change of the momentum is summation of force in the X direction equal to term here, okay? The first term is the unsteady term. And if you can see here, this is basically rho, right? And the volume here, the velocity here, and the change of the volume here. So it basically is the mass times, or the change of the mass within the control volume, okay? But now it is multiplied by the velocity. So the first term here is mass, and this term here is velocity. So similar to what we did for the conservation of mass, but now we are doing the conservation of momentum. So instead of like mass will be rho v, no, it's going to be like rho v is a volume. Now it's going to be multiplied by also the velocity. Okay, so the velocity times the mass will be basically the momentum. So the first term here will be the change of the momentum. And the second term here is basically how these masses crossing the, the boundary. So what is acting on the surface of this boundary? Okay, again, it's going to be like, the mass here that is crossing this boundary times the velocity at this boundary. Okay, same thing for Y, same thing for Z, which means that the conservation of momentum is those forces acting on the control volume will change the momentum within the control volume, and also, the rest of the change will be happening at the at the surface of these control volume. Okay. So what we need to do in this case is we need to monitor what's happening in any system. Let's first see if the system is steady or unsteady. So even it's a steady, only the first term will be 0, right? But the second term here will be a momentum in and momentum out. And I will show you example for this. So application for this very important topic is related to turbine or hydro production or hydraulic energy, right? So when you are basically having a lots of water at the back of the dam here at a very high level, we consider this level of fluids at the back of the dam is a stored type of energy. Okay, so you have a high potential fluid that is at a very high level, and now it's allowed to move in a pipeline. You can expect this flow in the pipeline to will be basically moving so fast. Okay, if you are able at some point at the exit of this pipe to even close the area a little bit, okay, and again we're talking general now, but we're gonna prove it in few seconds. Here is what's gonna happen to the velocity if we have a smaller area. Remember from the conservation of mass, if I have something like this, and this is Qn, and this is Q out, and this is a constant density fluid, AV out is equal to AVN, right? So what's going to happen if you are reducing the area in this case? What you are doing into the velocity? Right? You decrease the area, it will increase the velocity, right? And you've seen this in many times when you are holding a hose or something, and then you are closing the the opening of this hose or the nozzle at this nose, right? If you close it a little bit, the velocity will shoot up. That's basically because the same flow rate has to go out, but now we are reducing the area, so the velocity will go out. Okay, to the application of what we call it the hydro turbine, or for example, this specific type of turbine, we call it the Pelton wheel turbine. And this Pelton wheel is designed of a buckets like this. So this is kind of like a multiple buckets, and all are connected to a big rotor, right? So basically the jet will be basically going inside this bucket, hitting the bucket in order to rotate the turbine in this direction. Okay. So what's happening here is, if we consider this whole turbine is our control volume, now we are kind of, there is a momentum of fluid coming in, there is mass and velocity, right? And of course, this mass and velocity of the fluid that is coming from the, this downcomer here, or the pipeline here, will be going with a much higher momentum. So you have a huge mass going with a high velocity, right? So this momentum is basically allowing this turbine, or hitting the turbine blades or the turbine buckets, right? It will lose some of its energy and then will just go out, right? And what will be the momentum, transfer? It will be transferred to the turbine itself, right? So this is what we call it, the momentum transfer between the fluid and, the rotor of the turbine. Okay. Same thing here. When I think you might have tried this many times. If you have a balloon and then you fill this balloon with air, and then if you leave, the nozzle of the balloon out, what will happen to the balloon? Do you see what will happen to the balloon? Have you seen this before? Right. So if you have a balloon like this, right? You fill it, and then if you leave this open, what will happen? It will fly, right? Fly away in a different direction. What happened in this case? The air is going out of this nozzle or the opening of the balloon, right? Applying a momentum, So the change of the momentum of the system here is basically putting forces on the balloon itself in order to move it in the opposite direction. So you have a velocity here and the mass of flow going out, right? Similar idea of the rocket, right? You have a gas, you have a fuel here, and you have like, you know, oxygen inside. You are burning this and you are allowing this mass to go out with a very high velocity, right? So what will happen in this case is going to be some forces here. And these forces here is basically, you know, applied over this control volume of these rockets in order to move it in this direction. Okay, so the application of the momentum change in the fluids over a certain control volume there's so many applications for that. Okay, just to give you an idea about, like, you know, these turbine blades that we're talking about. Those are the buckets here, right? This is a turbine. Buckets here. We call it buckets here because this type of turbine is a very specific turbine. We call it belt-on wheel turbine, not kind of a blade kind of thing, right? But if you take a cross section here of this turbine, you will see this is a cross section of this bucket here. So, right, and it has, like, you know, a certain design that when you have a fluid that is coming in, right? So you have a fluid that is coming in here, it will go in the inside this bucket and it goes out here, right? So you're going to have some momentum because the momentum coming in, this is in, and of course this is out, right? Right? The change between the momentum coming in and that is going out, it will basically, you know, create forces on this, you know, turbine blade in order to, you know, generate this kind of, you know, torque or rotational power that we wanted out of a hydraulic turbine. Okay, so the application is massive in this kind of, you know, applications. Okay, in general, this is our equation for the summation of forces on any control surface. Of course, this is in the Z direction, but it could be in any other direction. Okay. First part here is within the control volume. What's going to happen? What is the momentum change within the control volume? And here, what is crossing in and out of the of the control surface? Okay. Some people here were asking about control system and control volume. Control volume is the whole volume of interest. Okay. Control system this is not what we are studying. We are studying only control volume. We are not following a certain mass. We are not going with the mass and see where this mass is going, right? We are kind of, we are fixed at a certain control volume and we are monitoring what's happening within the control volume at the surface of the control volume, which is what we call it the control surface, okay? Of course, for a steady state condition or a steady state flow, for example, in this turbine here, is always flow coming in and always flow going out, right? So we can call it, this is kind of a steady state type of problem. And you will see in many engineering applications, the steady state type of analysis are most commonly used in many applications, okay? So now if I have a steady state condition, what will happen to this equation? The steady state, what's going to happen to this equation? The first term will be, the first term will be 0. And now you only need to monitor the momentum of the control surface. It's becoming a very simple problem, right? You need to see the mass and the velocity of the, flow crossing the control volume in and out. And the change between these two is basically creating the force, right? As simple as your kind of, your understanding to the rocket flow that is going out. Of course, there is not so much N, right? Because the rocket is like, if it's in the space, so whatever is stored in the system inside is going to be unsteady problem in this case because the fuel inside is reduced, right? Right? So it's going to be much more complex, of course, than what we are talking about here, right? But you can imagine now, for a steady state problem, it's going to be only mass times velocity coming in and mass times velocity going out. The difference between these two will give you some forces, okay? And this is basically a simple simplified equation out of this. So you see here, this is, if you have only two surfaces, in and out is going to be 1 and 2. So I can now write the equation in general as external forces equal to the unsteady term, and the term that is crossing the the surface, the control surface, out minus n. Okay, let's solve a problem on this. We can appreciate what is the complexity of these type of problem. So we have, as you all see, all the aeroplane now is basically what you have: an engine, and this engine is it's on the wings, right? So you have all these engines running because of the combustion happening inside the engine, right? So you have fuel, you have air coming inside this inside this engine, and then so the air will come in this direction. There is fuel added inside the engine, and of course some sparks in order to start the ignition. And what will happen to the flow that is going out is going to be moving with, so this is out and this is in, right? So the mass going out here is going with, let's say if this is V1, so this will be V2. Okay, so what do you think about the mass that is going out here? Do you think the mass will go at a similar velocity of the aeroplane? Of course, this engine, imagine this engine is, of the aeroplane that is flying. So there is mass coming. It's going to be much higher, right? Why? Why? Oh, come on. I didn't even talk about the area here. Okay, no, just simple. Just think simple in this case. What I'm doing inside here, what I'm doing inside the engine here, what I'm burning inside the engine. Lots of combustion, right? Temperature is very, very high, right? So what's going to happen to the flow rate? So the gas that you are, right? You increase the temperature of this gas by so much. What's going to happen to this volume of the gas? If you want to, if you want to heat the gas too much, it's going to be like, the volume want to expand so much, right? But of course, it's not going to be expanding because there is no space to expand. So it's going to go fast, right? So this is what happened, right? And you are creating the thrust, right? We call it the thrust in this case. So the change of the momentum here is basically acting as a force to push the, the engine on the opposite side. Okay, but this is just to give you an idea about what we are talking about here. So let's read the problem. So the jet engine. So this is a jet engine typical for airplanes, but this jet engine on a test stand. So let's imagine this is basically a test engine that in the lab, right? So we are putting on the stand and we're testing this in the lab. So the air is stand figure admit air at 20 degrees C. So air here. So the air is at 20 degrees C. Air at 20 degrees C and 1 atmosphere. So pressure and temperature is given. Where A1 is 0.5 meters square. So the area is given, and the velocity 1 is 250 meters per second. Okay. So imagine, the airplane is moving with, if this is tested for an airplane moving at 250, that means you have to push air like, so much, right? So for the lab, we are allowing this air to go like, at 250. You are pushing air inside the engine at 250 meters per second. So what's happening after that? The fuel to air ratio is 1/30. So this is a fuel. Okay, so there's F fuel, right? And this is air, right? So the fuel to air ratio is 1/30. So the amount of fuel that you are kind of, adding is 1 over 30 of the amount of air that you are. So if you have 30 kilogram of air coming in, you will only have 1 kilogram of fuel added. Okay, as simple as that. So the air leave section 2 at atmospheric pressure. So the pressure B2 is also, so this is 1. B2 is 1 atmosphere, because this is a lab, right? So we are just working on this. Atmospheric and higher temperature. V2 is 900 meter per second, okay? And the area 2 is 0.4 meter square. So it just happened to be like, you know, it's almost like a nozzle here. So reduce the area, 0.4 meter per 0.4 meter square. Compute the horizontal test stand reaction, okay? Because what will happen if I don't fix these into the stand? If I'm putting this in the lab and I'm just running the engine, what will happen? The engine will just like breaking the, right? It just fly, right? So in order to do this testing, we are basically fixing this on a stand, right? And this stand is, you can see here in this picture here, is making a reaction here, reaction Rx, okay? So he's asking for how much this reaction is in order to hold the engine fixed, okay? So how can we start this problem? So let's put the assumptions first. Assumptions. Okay. What will be the assumption in this case? Do we have a steady state problem or no? Can I say that? You have a steady state? No? Why no? Why no? What is accumulating or what is changing inside this system? This system is running all the time, right? So so basically what we can do a steady state, because most of these open system that is in and out is a steady state, right? You will see most of the time unsteady is talking about tank is filling or tank is, you know, something like that, right? But in these cases, you know, there is going to be like a steady state. So if I put steady state, can I, you know, can I do anything else? Can I talk about density here as an, you know, incompressible or something? Can I put density here? No, right? Because basically this is air and the air is a compressible. So we have to find out the density of this air. But anyway, steady state mean that summation of the forces. And let's say this is our X direction. So summation of force in the X is equal to, remember this is basically what we're talking about, right? dm d by dt of the velocity rho dv, right, of the volume, plus what? The summation of momentum n, right? Or summation of momentum out minus summation of momentum n. Right? This is velocity and this is, right? So you have the mass flow rate and the velocity. This will give you the moment. This term here is 0 because it's steady. Okay. So I know what is the mass coming in and what is the mass going out. Do I know this values? Do I know what is the value of the mass? I have the area, right? I have the velocity. Do I have density? Do I have the density? Okay, how can we determine density? This is gas. This is air, so gas. What is the gas density? Yeah, remember I mentioned this in the chapter 1, right? Every time we're talking about gas, we have to remember there is another equation exists in, you know, in our science is called gas equation, right? VV equal MRT, right? So in this case, remember, like, you know, if you have BV equal MRT. So I know M over V is equal B over RT. This is my density, right? So if I know the pressure and temperature, I can find out your density. It just happened to know that, you know, the inlet here, rho 1 is what, like, you know, we have B1, T1, right? So B1 is 1 atmosphere. So remember, 1 atmosphere for this kind of equation, we have to be in absolute terms. So we have 101,300, right? Pascal. R for the air is 287. T for the air is 20 degrees C here is given. So 20 plus 273, right? Because it's an absolute. So this is rho 1. Rho 1 here is 1.205. Okay. I didn't mean to shut you down, like, you know, the people were talking about the table. Yeah, of course, if you go to the table, you find the density. Yeah, that's fine. But keep in mind that table always giving you a specific conditions. So you have to keep in mind that, you know, if you might have a different conditions, so temperature that is different or something, you have to calculate this, right? But of course, if it's 20 degrees C, which is the standard at the atmospheric, you can go and find it from the table, kilogram per meter cube. Okay. So can I get M1? So this way here is like, I can just summation of forces here. What is the summation of forces in this case? How many forces we have? How many forces we have here on this control volume? Four. Okay. What forces? What is the four? What is the four forces? Three. Okay. Anyone else? What forces we have here? What forces we have? Air in and out. I'm talking about forces. Reaction and thrust. Okay. Thrust is a reaction, because if you remove the holder, it will be the thrust. Drag on the turbine. I don't think you guys understand this. This is in the lab. So this is not flying. Okay. Atmospheric. I kind of imagine, like, you know, where are you coming from, right? Because you might think that the pressure around, you know, this engine, which is happen to be atmospheric, right? And it's everywhere the same or not. And the atmospheric, we're talking about gauges here, right? So what is the atmospheric pressure? Well, the air cause friction. What friction? In the wall, what fraction? We're talking about the control volume. This is my control volume, okay? And this is the control surface, okay? So this is external forces. This is not internal forces. This is external forces, right? You apply forces on this thing, right? So what is external forces here? It's only the stand, right? So this is the engine, fix it to this. So this is your extension force, right? So this is a control volume, the only external force. Do we have body force? Do you have gravity, for example? Do we have gravity for this engine? Why? This engine has a weight, of course, right? So if you are interested in the forces in the Y direction, right, we're going to include the external force as the weight of this engine, right? But now if you see this, this is what? This is the X direction, right? So the summation of force in the X direction will be equal to the momentum in the X direction. How about, the summation of force in the y direction would be equal what? Do you know? The summation of force in the y direction. Do you have momentum in the y direction? Do you have momentum in the y direction? Taha said no, right? Right? Everybody's saying no. Do we have other forces in the y direction if we are considering y direction? Yes, which is gravity, right? So if you are looking to find out the reaction in the y direction, you will see that the weight of this engine, but it's not given in the problem, so it's not really interesting here, right? We are not really interested in this value. We are interested on the reaction because of this momentum change. Okay, so summation of forces here would be, if I take this as a positive side, so it would be Rx, and now it's only one out, right? So it's M2 V2 minus, it's only one N, which is M1 V1. Make it looks the same. Okay. So we have mass coming in and mass going out. So what is the mass one? We know the density one, right? Times area 1 times V1. This will give me mass 1, right? So I know the density is 1.0, or sorry, 1.205 times the area is given as 0.5 meter square times the velocity here is 250. I can calculate this to be 151 kilogram per second. Okay. Can you tell me what is M2? Is it V1? Yeah, V1. Yeah. Yeah, V1, the velocity. Yeah. Okay. Can you tell me what is M2? In M1, yes. V1 in M1, we means. Yeah, that's fine. But I'm just getting the mass, only the mass. Yeah. Oh, I'm sorry. Yeah, you're right. I like that you're insisting to correct me. Thank you. Sorry, it's yeah, the mass 2 and yeah. Thank you. So the mass 1 is 151 kilogram per second. Okay. Can you tell me what will happen into can you tell me what happened to the mass 2? Is it going to be the same value? Do you think so? No. Why? Because it's a very specific given in the problem. You remember? Yeah, higher temperature. This is mass could be the same, but the higher temperature doesn't matter. No, nothing about it. It's a ratio. You see, remember the ratio of the fuel? He's telling you actually you have a fuel here, and you cannot ignore it. Okay. So if he didn't mention anything about it, like we might really consider M1 is equal to M2, right? Because there's nothing given about like what's happening in the combustion engine, right? But it's specifically in this problem is telling you that you have an air to fuel ratio of 1/30, right? Let me add here. So air to fuel ratio is 1/30, right? Which means that if you have a certain mass that is coming in, so mass of the fuel here should be what? 1/30 times 151, right? Because for each kilogram of air, you are adding 1/30, right? So you can find out M fuel here, right? So M fuel here is, I think it's like 5, right? Right, it's 5 point something, right? So what will be the mass 2 here? Mass 2 here will be M1, right? Plus M of the fuel, right? This is basically the conservation of mass. So I'm doing this conservation of mass very quickly now. Why? Because I don't have to really write the whole equation and unsteady and all this, right? It's just whatever coming in is going out, right? Because steady state. So N is two things, N, air and fuel. And the fuel is 1/30 of the N of the air, right? So it's basically 1 plus 1/30 of the air, right? So this is basically what happened here. So you have m.1, which is 151 plus 1/30 times 151. This will give you about 156 kilogram per second. Okay. So I go back to, equation this, right? So into equation 1, reaction here is equal to m dot 2 V2 minus m dot 1 V1, right? M2 here is 156 times 900 minus M1, which is 151 times 250. And this will be 102.123 Newton, or 1.102 kilonewton. Okay. 1/30. You have it flipped? What do you mean have it flipped? Don't, okay. Don't make me, be confused. What do you mean? Air to fuel ratio? Oh, sorry. Air to fuel ratio is 30. Or fuel to air ratio is, yes. Thank you, guys. I'm moving fast today. So air to fuel ratio is 30. Right? Or fuel to air ratio is 1/30. Thank you. Okay. But the answer is correct. M fuel here is like 1/30 of the air, right? So we have 102 kilonewton. Okay. So why did we do minus? What is minus here? Yeah, what is minus? Yeah, I don't think in equation 2. Okay, anyway, this is equal. Sorry, guys. I like you being very, precise on this kind of things, but this is good. So we have a reaction of this engine that is about like 102 kilonewton, right? So you can imagine the massive amount of reaction because of the thrust or the change of the momentum. So you can understand from this subject today is like, once we have a momentum of fluid coming into the system and going out, the change of this momentum is actually creating forces on the object itself, right? So you will see this in many applications. For example, the sprinkler system, right? When you have a sprinkler system in your yard, right? You have this, jet coming out, and this jet is going out like this. So it's kind of like moving this into, if you have a rotor or something. Yeah, so the jet going out is kind of, pushing this nozzle to keep rotating and stuff like that. So you can use the momentum in order to create some forces that you can use in your engineering applications. Okay. Any questions before we move to why don't we find the new density of M2? I don't need, right? Because I get M2 as a summation of M1 and M2. I know M1 and I know how much M fuel is. So I don't need like the density, the second density. How do you know the air to fuel ratio is mass or not volume? And this is a very good question, Colin. And I apologize for whatever written on the problem. It should be written in a way that, is giving you an idea about this, because the people are like interested in combustion. They will find out sometime this air to fuel ratio is given by volume flow rate, not by the mass. But that's a good question. We have no option in this problem, to be honest, in order to use it as a volume, because we don't know what's happening inside this engine as well. So we will consider it as a mass. Yeah. What are two value for the denominator? BV, MRT, RT. RT, that R is the gas constant, and it's air in this case, 287. And the T is a temperature in absolutes. Okay, so we need to move a little bit. 8.13, this is a universal gas constant, and please go back to our first chapter. I specifically mentioned that if you have a, MRT, that means M and R is a specific gas constant, and this is air, so it's 287. But if you have 8.3, this is universal, so you have to, so you have to divide by the molecular mass, and then you multiply by 1,000, so we'll give you the 287. Okay. Can we move into actually today's lecture? Because we're kind of behind a little bit. Okay. It's kind of a continuation to what we are talking about in terms of the fluid flow in the system, and we need to find out fundamental principle of these fluid flow analysis. So, and also still using the control volume approach. We did this for the conservation of mass and the conservation of momentum. What we're gonna do today, or this part of the slides, talking about the conservation of energy. Okay. And we are talking about linear momentum because I don't think we will have time in our course to cover many things. As I mentioned to you, there is so many fluid mechanics courses. This is just the first simple one, right? So you might even look at the change of the momentum and the change of the of the energy in terms of cylindrical coordinates. So if you have some kind of rotational kind of device, the same way as a turbine. In the turbine, we are considering rotational motion, so we might need to do the analysis a little bit differently, right? But of course, this for this course, if we at least understand the fundamental principles, the people are interested can learn the expansion by themselves. It's not going to be a big a big step of effort to do that. So today's lecture is talking about something called the Bernoulli equation, and the Bernoulli equation is a specific or a specialized equation of the energy equation, assuming very important thing. Remember when we talk about ideal flow? What was the ideal flow is referring to? Okay. What was the ideal flow referring to? Anyone remember our last conversation? What? Ideal flow, guys. You guys kind of bringing any general words from what we're talking about. Ideal flow. Ideal flow. We spent time last time talking about this. Ideal flow. Ideal flow has nothing to do with conservation of mass. Anyway, so let me remind you with this. We talked about something called ideal flow last time. It's friction. Thank you, Matthew. Thank you. Thank you. Somebody remember. Okay. It is talking about friction. So ideal flow never exists. We just assume it for some cases in order to simplify the problem, right? And simplification is not bad. Actually, the very good engineer is the one who is able to simplify the problem and provide the answer very quickly, right? But sometimes simplification has to be at a different level. So you can go with so many simplification and then come up with an idea about what's happening, and then you add one level of difficulty as you building your knowledge and as you are building your model, right? And it's all depend on how can you what kind of time limits and resources you are available to you in order to provide an answer, right? Because sometimes you are in a situation when you need to really move fast and just do a quick calculation to find out where are you, what kind of range you're looking at, right? So Bernoulli equation is considered one of the very famous equation in the fluid mechanics topic. And the Bernoulli equation is an analysis for the pressure, velocity, and elevation on basically, but in a frictionless flow. Frictionless flow has no friction, right? It's basically as we assume viscosity is zero. right? So there's no friction, which is, in this case, is not the true case, but it is like, it is a very good, kind of approximation when we are looking into general idea between, like, what is the percentage of different energy in the system and so on. So the complete derivation of this equation was given by Leonhard Euler, and that's why Euler equation is the first integral form of this Bernoulli equation, right? So this analysis or the derivation came first by Euler, and it's called Euler equation, and then Bernoulli is kind of expanded this analysis in order to basically apply it over a certain condition in the fluids in order to represent something called the conservation of energy equation. Okay, so it is about conservation of energy, so energy in and energy out, and the change of the energy within the system. Similar way as we did the conservation of mass and the conservation of momentum. So in order to understand how Euler equation is developed, right? I'm going to go a little bit, deeper here because it's very important. So what we have is, like, we have an element. Let's talk about an element like this. So imagine this is your L, and this is, the longitudinal length along the, the fluid type of flow. And if I'm taking an element here along this L, the nice element to take in order to do this is basically a cylindrical point. And this is what Euler is basically. Starting from the second law of Newton too, right? Summation of forces equal to mass times acceleration, right? But the only important assumption here is no viscous forces. So if this element is moving in this direction, there is no viscous here. So friction here is zero, right? Because if this element is moving, it should be resisted by some friction or viscous friction of the fluid. In this case, because we are considering frictionless fluids, we have no friction forces here, right? So if I look at the forces applied on this element, is going to be a pressure from this side, and the pressure will be inside this side as well. And if you remember, when we talk about pressure always going to the area, right? So if I'm taking an element like this, so when I'm talking about this area, the pressure will be going inside. When I'm talking about this area, the pressure is going to be inside here. If this element has a differential area is dA, so the pressure forces will be the pressure times delta A. From the other side here, after a certain point L, the pressure has to be changed, like, it's going to be a certain value, right? How much is this value? I can consider to be the same value of these points, like let's say 0.1 here, is going to be the same value plus some change, right? So in general, so I have a pressure here that is B delta A, and I have a pressure here that is B plus delta B, but because multiplied by the same delta A, because this is a cylinder, okay? And the length of this element is delta L. So again, we are talking about like a differential element. So I'm talking about a very small little element, okay? This element has a weight, right? And the weight here in general, if the element in whatever alpha angle, it's in a general direction, the weight here will be delta W, right? And basically delta W is basically see what is the volume of this element and also the density of this element. You can find out the weight of this element, okay? But apparently here, because the weight is acting, of course, normal in the gravity direction, right? And we are interested in this direction. So I have to take the elements, the component of this weight. One will be, if this is alpha, it will be cosine here and it will be sine here. And it's going to be in this direction here. So it's going to be delta W sine alpha. Sine alpha is very simple, right? Because if you have Z and you have alpha and you have delta L, so sine alpha is delta Z over delta L. Very straightforward. Now, when I look at the summation of forces here, I have forces that is pressure forces, and I have, gravity forces. And that's why pressure forces here and the gravity forces here equal to mass times acceleration, okay? And the mass is, of course, is volume times density. So the volume is delta A delta L times density. Okay, so I have now the summation of forces equal to mass times acceleration, right? The summation of forces is pressure. Pressure is this one here in this direction, this one here in this direction. So I can find out first the pressure forces. The pressure forces is B delta A. So this is a positive direction. So this is positive. This is minus B plus delta B delta A, right? So this will be the pressure force. It looks like this term here will be canceled by this term here, right? The gravitational forces, if you remember, it is the component of the weight delta W sine alpha. Okay, so it's for delta W sine alpha, and delta W is what? It is basically the mass. This is the mass. So the weight will be mass times the gravitational acceleration, right? So you will see here, the density times the acceleration is rho g, which is specific weight. If you remember, the specific weight is rho g, right? So if gravity is that much, if pressure is that much, now mass, okay, so I just put the whole equation now is equal to, this is the mass times acceleration, right? So this term here will be gone with this, right? So, and this will be delta B, delta A, right? There's going to be gamma, delta L, delta A sine alpha, this term here. So I can divide the whole equation by delta A, right? So, and also delta L, the whole equation. So this term here will be basically delta B over delta L minus gamma sine alpha equal to rho times the acceleration. And the acceleration here in the L direction, okay. So now I can convert all the delta, right? If I take the limit. So if I have a component or a small little elements, as much as this element gets smaller, the delta or in the mass operator will become differential, right? So I can change this operation here from delta to delta if the element is become very small. So whatever delta, I can change it to d by d, right? So dz by dl. So now I'm converting this whole equation into dB by dl minus gamma dz by dl. You remember this sine alpha is, you see sine alpha here, delta z, right? Equal to rho times acceleration. Now I have an equation simple like this, right? I can take the operator as a common between the pressure plus gamma z is equal to rho times acceleration, right? So the equation now is becoming this way, right? I can do the same thing along any path, S path in general, right? One thing that we have to know about acceleration is change of the velocity, right? But this is, if you remember in your mass, acceleration is d of the velocity with respect to d time. Remember, this is total derivative, right? But this is partial derivative, right? That's why the velocity in general could be function of space and time, okay? That's why the acceleration is, when we differentiate total, it's basically, if you remember, when you have a function that is, or that is a function of two variables, when we take the derivative of this function or the total derivative of this function, it is going to be like the first one times the derivative of the second one plus the second one times the derivative of the first one. So you will see that the acceleration is actually two parts. One part is, we call it the convective acceleration, and the second part we call it the local derivative. The first one that is function of ds, the second one will be the derivative with respect to the time. Okay. So for a steady flow, it looks like this term here is 0. So how come acceleration will be still some value here, right? Although the steady incompressible fluid, right? You have to remember that we are talking about total derivative, and total derivative here is the velocity can change with the location, not with the time. Okay, so what happened here in this case, I can just take this term here and just put it in this, sorry, I can put it in as a function of this term here, right? For a steady state incompressible fluids. So now acceleration will be v dv by ds. Okay, so if I have v dv by ds, I can take the v and put it inside the derivative. This will convert it into dv square over 2 over ds, right? So now this term here now become this is equal to rho d by ds of v square over 2. Again, I'm going through what Euler has kind of developed, right? So this is how we come up, this is how we come up with the analysis of the pressure forces and the change of the momentum or the acceleration, or along a distance L or along the path S in general. So you will see here that this is d by ds of the pressure plus gamma z is equal to rho d by ds of v square over 2g. I can rearrange this in one side. So it's going to be d by ds, pressure gamma z plus rho v square over 2. And this will be equal 0 because I put this on, or I put this on this side here, right? So what is this telling you? It's telling you that along any path, right, d by ds of these three terms is equal 0, which means that the integration here is with respect to s will be this term here, and the integration of 0 will be constant. So, and this is basically what is the Euler equation is saying. You have a summation of three terms, and those three terms are constant, only for frictionless flow. Okay, remember that the first assumption that we don't have shear forces here. We didn't take the shear forces here, right? When we apply the forces, right? So Euler managed to come up with an equation, okay, that is telling you that the summation of three energies, three terms, we call it now, we're gonna call it something after a few seconds here, right? Those summation of three terms are constant along any path of the fluids, as long as the flow is considered to be frictionless, okay? Which means that at point 1 and point 2 and point 3, the summation of these three terms are the same, right? That's why those, right? And this equation, the difference between this equation and this equation is we divided by rho g, right? Just like normalize the equation by rho g, right? So you see here, this is B1 divided by rho g. Rho g is gamma, right? So divided by rho g or gamma, right? Because both are the same. So I have B1 over rho g plus Z1 plus V square over 2g at point 1, and this is at point 2. Okay, and this is what we call it the Bernoulli equation. So remember, this Bernoulli equation is developed from this analysis of Euler, right? But we have to make sure that we understand that these whole equations are developed for a steady state flow, incompressible fluid, because we are not considering any change of the density in our analysis, frictionless flow, along a path, along a certain flow direction, right? So we call it a streamline. So in chapter 4, we're going to talk about this in more detail, but at least, for this chapter here, we need to know that Euler equation is an equation that is relating three types of energy. The first one is related to pressure. The second one is related to the potential or the height Z. And the third one is related to the kinetic energy. So, and those three equations, those three terms of energy are constant if we have a steady, incompressible, frictionless along the path line, along the streamline. Okay. So next time, I guess, because I am, I lost all the time now. So I think next time we're going to talk about something called hydraulic gradient line and how can we apply the Bernoulli equation. Any questions? Let me stop recording, and if you people want to stay around, just ask a question, you can do that. Stop recording.